All right, we are going to get started with section 1F, classifying and ordering numbers. So the first key concept we're going to look at are square roots. So the square root of a number, the definition is this, and it's kind of confusing, but bear with me. So if b squared equals a, then b is the square root of a. For example, it makes a whole lot more sense when we have numbers. 3 squared equals 9, and negative 3 in parentheses squared equals 9. So 3 and negative 3 are both square roots of 9. So basically, when you take a number and you square it, for example, like 4. If I take an integer like 4, which means no decimals, no fractions, and I raise it to the power of 2, which means squaring it, that answer here is 16. And the reason why I'm going over it this way is because 16 is a perfect square, since we can take a number and square it and equal 16. And the opposite of taking something and squaring it is taking the square root, and the square root looks like this. You take the square root of 16 and it equals 4. It basically says take a number and divide it, not by 2, but divide it by a number that when you multiply that number by itself, it equals 16. So that number by itself, 4 times 4 equals 16, so the square root of 16 is 4. It only works when we have perfect squares. Looking at the next part of the notes, it says all positive real numbers have 2 square roots, a positive square root, or a principal square root, and a negative square root. A square root is written with a radical symbol. The number on the inside is called the radicand. So, like I said here, the square root of 16, this right here is pointing to the radical symbol, and 16 is considered the radicand. Okay? Moving down to the next part of the notes. It says here that 0 has only one square root, 0. Negative real numbers do not have any real square roots because when you take a square root of a number, both of those numbers have to either be positive or both of those have to be negative. If you tried this in your calculator, the square root of negative 4, your calculator will tell you that there's an error. It does not work. And that's because when you are multiplying these numbers to get the answer, you have to have the same number. It can't be different numbers. And when you multiply, 1 positive times 1 negative equals a negative, and those are different numbers. Okay, so for example, evaluate the expression for the positive square root. So the negative, the opposite of the square root of 9. Well, the square root of 9 is asking us to find what number times itself equals 9. That's what the square root does. Well, 3 times 3 equals 9, so I know that the square root of 9 is equal to 3. Because we have this negative here, that means what's the opposite of the square root of 9? So this final answer would be negative 3. The square root of 25 says what number times itself equals 25? And that is 5, since 5 times 5 equals 25. For the next one, the square root of 64. What number times what number equals 64? That is 8. And then number 4 is the opposite of what the square root of 81 is. Well, 9 times 9 is 81, so I know the square root of 81 is 9. So the opposite, negative, of the square root of 81 would be negative 9, like that. In the next examples, we are approximating the square roots to the nearest integer without using a calculator. This is really helpful if we list the square roots. The smallest, and make sure you're writing this in your notes as well, the smallest perfect square we have is 1. And I'll write here perfect squares. The smallest perfect square is 1, since 1 squared is 1. Moving down the line, if we take 2, the next positive integer, and square that, then the answer is 4. The next perfect square is 4. And then if we do this process again, we do 3 squared. The next perfect square then is 9. 4 squared. The next perfect square is 16. 5 squared. The next perfect square is 25. And we can keep going and continue on this list to get these perfect squares, but the perfect squares are on top of them. The next one is 36. you, but these are our first 10 perfect squares, and the perfect squares are the numbers above. So all these numbers here are all of our perfect squares. The way we get perfect squares is by taking an integer and squaring it. Okay, so that will help us with this next section that's asking us to approximate the square root to the nearest integer. So that means for the square root of 32, we're looking for which perfect square is closest to the radicand 32. Well, the closest number I see is here, 36. So 36 is 6 squared. That means 6 times 6 is 36. That also means since 32 is closest to 36, then this has to approximately be, this is an equal sign that's kind of squiggled like that. That means approximately. I would say it's approximately closest to 6. Now, if I do use my calculator, just so I can show you, when I put the square root of 32 in my calculator, this is 5.6568, so on. So it's 5.7, let's say, which is approximately 6. Okay? Moving on to the next one. The square root of 103. So I'm looking at my perfect square list, trying to find a number closest to 103, and that's 100. 100 is a perfect square since 10 times 10 is 100, or 10 squared is 100. That means that this is close to 10. When you take the square root of 103, it's going to be approximately 10. All right, the square root of 48. We're looking on our list here for a number closest to 48, and 49 is a perfect square, which is closest to 48. Now, this number is asking for the opposite of the square root of 48, so I know the answer is going to be negative of whatever the square root of 49 is. So it's going to be approximately negative 7, since 7 squared is 49. Then the square root of 49 is 7. The negative square root of 48 would be approximately negative 7. All right, in the last one, we would have to keep going on with this list here to determine the perfect squares for a number this big. So I can tell you that 18 squared is 324, and 19 squared is 361. So that will help us determine where this answer is going to be for the negative square root of 350. So 350 is closer to 361 than it is 324. So that means that this is going to be approximately negative, since the negative sign is here, negative 19, since 19 squared is 361. Okay. If we flip this over, the next part of this lesson is classifying real numbers. So let me erase this. And scroll down. Okay, so perfect squares we actually already went over, but we can list these again. The smallest perfect square is 1, since 1 squared is 1. 2 squared is 4, 3 squared is 9. 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, and we could keep going. We could keep doing that forever, but we'll just list those first 10 ones. So perfect squares, I guess I should have put that in the examples row, but that's fine. The definition of a perfect square, the mathematical definition is a little bit confusing, so let's just do some definitions that might make a little bit more sense than the real deep math definitions. So a perfect square is when you take an integer and you square it. It then becomes a perfect square. And the reason why we call it this is because if we actually take a square, we know that squares have equal side lengths. So in every square, I know the length is equal to the width. So if we take this square and we say that this length is 3 centimeters and this length is 3 centimeters, all of the lengths are 3 centimeters, and to find the area, you multiply the length times the width, 3 times 3, and you get 9. That means that this area has an area of 9, and 9 is a perfect square. That's where that comes from. All right, also classifying numbers, the next thing we have is rational numbers. In the word rational, we see the word ratio. And you might be thinking, oh, ratio, I remember what that means. That means a fraction, right? Yes. A rational number is a number that can be put into fraction form. So I'm writing down a number that can be put in fraction form. Okay, there's tons of numbers that can be put in fraction form. Fractions itself are already in fraction form, so an example of a rational number could be like 2/3. That's already in fraction form, so it's a rational number. Or just like a plain old number like -7. -7 can be put into a fraction. I could do -14 divided by 2, or -14 over 2. That equals -7. Rational numbers can be positive, they can be negative, they can be in mixed number form, like 1 and 1/5. That could be put in just one plain fraction. It could be something that is a square root, like the square root of 16. The square root of 16 is 4, and since 4 can be put into a fraction, the square root of 16 would also be considered a rational number. So we can have positive fractions, negative fractions. They can look just like whole numbers with no decimals or anything like that yet, but they also could look like in decimal form, like 1.5. 1.5 can be put into a fraction. That's 3/2. So basically, rational numbers are any number, and no matter what form they're currently in, any number that can be put into a fraction is considered a rational number. An irrational number is a number that cannot be put in fraction form. So the way that you can tell a number can't be put in fraction form is by seeing that the decimals are crazy. So the decimal numbers in a number that can't be put into fraction form, the decimals go on forever. Okay, so that actually, the fancy way for saying that is that they never terminate. And they also, they never repeat the same pattern. So irrational numbers are numbers that are hard to deal with. The most commonly used irrational number is pi. If I take if I put pi in my calculator and hit enter, it's going to tell me that pi is equal to 3.1415926, and it keeps going on forever and ever and ever. Those decimals never end. Literally, there's a calculator right now continuing to pull up different numbers in pi, and what's very interesting is that the pattern of those numbers never ever change, or never are the same. They're constantly changing. So we don't have a certain pattern that we'll be able to track and see, and when these numbers do have a pattern, you can put it into a fraction form. So like for example, 2/3 up here. 2/3 is a rational number, but if you look at your calculator and you do 2 divided by 3, your calculator says 0.666666, and so on. Well, that pattern does repeat, and when you have repeating patterns, that means that it can be put into fraction form. Non-repeating patterns means it cannot be put into fraction form. Another example of numbers that do not ever stop or repeat the same pattern are irrational numbers that are like the square root of any number that's not a perfect square. 2 is not a perfect square because there's no number you can divide and multiply this integer by this integer to equal 2. If I look at my calculator, the square root of 2 is 2, 1, 3, 5, 6, 2. And again, these numbers go on forever. They never stop. They continue on to infinity. All right? And then the next set of numbers we have, let me just erase this real quick, are real, does it say real numbers? Hold on, let me erase and scroll. Please erase. Great. All right, so the next and last one we are going to do are the real numbers. So real numbers are actually the set of numbers that are rational and irrational. So real numbers are all rational and irrational numbers. So that means any number that we deal with in algebra is considered a real number. Okay. At this point, we are going to stop and we are going to complete some examples together in our packet.